In this video, we are going to look at geometric sequences, and we're going to look at them in explicit form. I have a geometric sequence written out here. It goes 3, 6, 12, 24, and so on. And the thing that makes this a geometric sequence is that we have a common ratio in between each two terms. So, for example, in order to go from 3 to 6, I would need to multiply by the number 2. And in order to go from 6 to 12, I would need to also multiply by the number 2. And to go from 12 to 24, again, I'm multiplying by the number 2. So each term in this sequence is defined by the same operation of multiplying by 2. That's what makes this a geometric sequence. Now, there are lots of ways that we can write out geometric sequences. One is just writing out the numbers of the sequence themselves, but we can also write a formula or an equation that describes the sequence of numbers, and that's what we're going to do now. So in order to write out the explicit form of a geometric sequence, I need to know two pieces of information. The first piece of information I need to know is the starting value. And you'll notice that I have 3 written in yellow here because 3 is the starting value of this sequence. So let me write that out. We have our starting value, and that is 3. That's what we start with. You might also see the term initial value. And then the other piece of information we need in order to define our geometric sequence is our common ratio. It's not an M, common ratio. And our common ratio is what we multiply at each step in order to create or define the next term in the sequence. And so the common ratio here, for this sequence, is 2. These are the two pieces of information that define this geometric sequence. Now, let's say, actually, before we get to that, let's define or name each of these terms. This is a sub 1. This is a sub 2 because it's our second term. This is a sub 3 because it's our third term. This is a sub 4 because it's our fourth term. And if we were to write out a sub 5, it would be right there, and so on. Now, we always start with a sub 1 as our starting value, so let me label that here. This is a sub 1. And in other classes or in other demonstrations, you might come across a sequence counting that starts with 0, and so your first term is a sub 0 and then a sub 1 is your second term. I think that's a little bit confusing for this introduction, so we're using a sub 1 for our first term and a sub 2 for our second term, and so on. And let's say that we wanted to find out what a sub 7 was. A sub 7, or in other words, the 7th term in our sequence. Well, we could write out our starting term, or our starting value, which is 3. And then notice that in order to get to the next step in the sequence, we're multiplying by 2 at each step. And so in order to get to our second term, we multiply by 2. In order to get from our starting value to our third term, we multiply by 2 times. And to get to our fourth term, we multiply by 2 3 times, and so on. And so when we write out this formula here, a sub 7 is going to be equal to 3, and then times our common ratio. And how many times are we going to do it? Well, we're going to do it 7 minus 1 times. 7 minus 1 times. And that's the same reason that if we're trying to find out what a sub 5 is, for example, then we would start with our starting value, and then we would multiply by 2, and then again by 2, and again by 2, and again by 2. And so a sub 5, our fifth term, we have 4 multiplications by 2. For a sub 6, there would be 5 multiplications by 2, and for a sub 7, there would be 6 multiplications by 2. And so that's why we have 7 subtract 1 here. And so in order to find out what a sub 7 is, we just need to simplify this. And so we have, let's see, I'll continue the colors here. We have 3 times 2, and that's to the 7 subtract 1 power, or the 6th power. And let's see, 3 again times, and remember, another way that we can think of 2 to the power of 6 is just 2 times 2 6 times, because exponents are just repeated multiplication. So we have 3 times 2 times 2 times 2. There's 3 2's, and 4 2's, 5 2's, and 6 2's. So these are equivalent expressions. They mean the same thing. And you could get out a calculator and calculate this out if you don't know it off the top of your head. 3 times 2 times 2 times 2 times 2 times 2 times 2 is 192. So that's a sub 7. It's equal to 192. And just to reiterate here, we have our starting value of 3, and then we're multiplying by 2, 1 less than whatever our number, the number of the term is that we're trying to find out. So if it's a sub 7, we multiply by 2 6 times. If it's a sub 10, then we multiply by 2 9 times. That's why we have this subtract 1 right here. So let's write out the general formula for a geometric sequence in explicit form. So we have a sub some number, sub 2 or sub 10 or sub 20 or whatever. And that is equal to our starting value, which is a1, remember, a1. And then we're going to multiply that by our common ratio. This is a multiplication sign here. We're multiplying that by our common ratio, which we'll call r. And I'll label this up here just to be consistent. And that's multiplied by our common ratio. And then we raise that common ratio to the power of n subtract 1. So this is our general formula for a geometric sequence in explicit form. And so let me put a nice red box around it, and then we can work some examples. Okay, so let's say that I have a sequence that goes -1, and then -3, and then -9, and then -27, and so on. Okay, so the first thing that I want to do here is I want to identify my starting term or my starting value, and that is -1. So I have a starting value of -1, and then I also want to identify my common ratio. So what is the number that I need to multiply by in order to go from one step to the next here? So -1 times what is equal to -3? Well, -1 times 3 is equal to -3. And then -3 times 3 is equal to -9. And -9 times -3 is equal to -27. So my common ratio here is 3. My starting value is -1. And so we can write out our formula for this, or our equation, as a sub n, so in other words, some term in the sequence is equal to -1, because that's our starting value, so let me be consistent with the colors here, -1 times, I'll do this in white and then green, times our common ratio, which is 3, and then all of that to the power of n subtract 1. And let me make this n purple. We have n and then subtract 1. So this defines any particular term in the sequence. So if I wanted to find out, for example, what the 10th term in the sequence was, that would be a sub 10, then all I need to do is replace n in my formula here with 10 and then simplify. So I have -1 times 3 to the 10 subtract 1, and that is equal to -1 times 3 to the 9th power. And let's see, 3 to the 9th power, I calculated this on my calculator, it's 19,683, and we take the negative of that. So we have -19,683. That is the 10th term of this sequence, or a sub 10. So this is a sub 1 here, a sub 2, a sub 3, a sub 4, and so on and so forth. A sub 10, this term right here, is equal to negative 19,683. Let's do another one. Let's say that you, instead of being given the actual terms of the sequence, you're given the equation for the sequence. And it is a sub n is equal to 64 times 1/2 to the power of n subtract 1. So this is the explicit form of some sequence, and we want to write out what this sequence is actually equal to. Actually, before we do that, let's find out what the second term in the sequence is. Let's say we want to find out what a2 is equal to. So as always, the two things that we want to figure out are, we want to figure out what our starting value is, and we want to figure out what our common ratio is. So our starting value is 64, and our common ratio is 1/2, this part right here. And so if we want to find out what a sub 2 is equal to, all we need to do is rewrite what we have on the right-hand side here and substitute in a 2 where we have n. And so let's work that out. We have 64 times 1/2 to the 2 subtract 1 power. And so that is equal to 64 times 1/2 to the 2 subtract 1 power is 1. And anything to the first power is just itself. And so we have 64 times 1/2, which is equal to 64 divided by 2, which is equal to 32. And so we can write out the first term and the second term of this sequence. We know that the first term is 64. We know that the second term, or a sub 2, is 32. And we're halving at each step, and so half of 32 is 16. Half of 16 is 8, and so on. It continues from there. You might recognize this sort of pattern from our unit on exponential decay. So again, this is a geometric sequence represented in explicit form. We have two pieces of it. We have our starting value, which is a sub 1, and then we multiply that by our common ratio, which is r raised to the power of n subtract 1.